Hey everyone, and welcome to this Tech Details Explainer. I am so thrilled to have you here today. Our goal for this one is pretty simple, but really exciting. We are going to completely demystify the magic behind data storage. We're going to explore exactly how databases store, organize, search, update, and retrieve absolutely massive amounts of information. I mean, we interact with these systems every single day, right? But they operate almost entirely behind the scenes. So today, we're going right under the hood to see how the engine actually works. Okay, let's dive into this with a super relatable scenario. Picture this. You're browsing an online store, you find the absolute perfect pair of headphones, you add them to your cart, and you click buy. In that exact millisecond, a highly choreographed dance of digital information kicks off. Your user profile, the store's product inventory, your order history, and your payment details, they all have to be processed, updated, and safely secured. And hopefully without your credit card declining. But really, how does the system handle all of that so seamlessly? To figure that out, we're going to break this down into 5 parts. First, the anatomy of databases. Second, the journey of a query. Third, the need for speed. Fourth, guaranteeing data safety. And fifth, scaling the system. Starting right off with Section 1, the anatomy of databases. Before we can track your shopping cart's journey across the internet, we really need to get our heads around the fundamentals. At its core, a database is a specialized system designed to efficiently store, organize, and retrieve data. Now, you might be wondering, why not just use a plain text file or a normal spreadsheet on an operating system? Well, while a text file is totally fine for your weekly grocery list, it literally falls apart when millions of users are trying to read and write data all at the exact same time. Databases are purpose-built software engines carefully crafted to securely and rapidly handle massive complex data structures without buckling under the pressure. And this brilliantly illustrates how a traditional relational database handles that information. It structures data using tables containing rows and columns, kind of like a highly organized digital ledger. Each column is an attribute, so product name or cost, and each row is a specific record. You'll notice that product_ID is marked as a PK, which stands for primary key. That's simply a unique identifier. We can also use what are called foreign keys, like linking a customer_ID in this table over to a completely separate table that holds all the user profiles. That connection right there, that is exactly how the database links your specific user account to those $100 headphones you just bought. Now, not all databases are built quite the same way. We essentially have 2 main camps. On one side, we've got relational databases, which speak a language called SQL, structured query language. Systems like MySQL and PostgreSQL live in this camp, and they're all about enforcing strict tabular structures and keeping data integrity super tight. But on the flip side, we have non-relational or NoSQL databases like MongoDB or Redis. Instead of rigid tables, they might store your data as flexible JSON-like documents or even just simple key-value pairs. Basically, they trade some of that structural strictness for incredible flexibility, which makes them absolutely fantastic for applications where the data is constantly changing. Let's move on to Section 2, the journey of a query. So let's track exactly how data flows from your screen all the way down to the physical hard drive. When you hit buy on your web browser, that action zips across the internet using HTTP or HTTPS protocols until it hits the application server. The application then turns around and talks to the database through an API over the network layer. Once the database server gets this request, it hands it off to the database engine, processes the query, grabs the data from storage, and fires the result all the way back up the chain to your screen. And the craziest part? This entire round trip usually happens in just a tiny fraction of a second. But how exactly does the application ask the database for your specific headphones? Well, if it's a relational database, it speaks SQL. It sends a command that looks exactly like this. In plain English, this translates to a very direct instruction. Go into the inventory table, find every single piece of information you have on the product with the ID P1, and give it to me right now. But what's actually happening inside the database the moment it receives that SQL command? It goes through a really strict execution pipeline. First up is tokenization, which chops the sentence up into smaller recognizable words or tokens. Then parsing kicks in to check the grammar, essentially making sure you didn't make any syntax errors. Next is optimization. Think of this as the database's brain figuring out the absolute fastest, most efficient path to fetch your data. And finally, the execution engine takes that highly optimized plan and actually runs the operation. Which brings us perfectly to Section 3, the need for speed. Think about a massive e-commerce giant. They might have tens of millions of products. So how on earth does the execution engine find your exact $100 headphones out of millions of records in mere milliseconds, without just mindlessly scanning every single item one by one? The secret is an incredibly clever internal data structure known as an index, specifically the B plus tree. Whenever you add an index to a database column, the system builds this tree right behind the scenes. It's what we call a wide tree, meaning nodes can have multiple children, and it's perfectly balanced. Because it stays balanced, it doesn't matter if you're searching for the very first product in the database or the 10 millionth, the search path from the top to the bottom is always the exact same length. It helps to think of the B plus tree in two distinct parts. The upper levels are the internal nodes. You can think of these strictly as a navigation GPS. They don't actually store your data. They just hold boundary keys that say, hey, values lower than 1,000, go left, values higher, go right. They just point the way. Down at the bottom level, we have the leaf nodes. This is the actual data warehouse where the records live. And here's the brilliant part. These leaf nodes are linked together horizontally in a chain. So once you've found your starting point, scanning through a whole range of products is incredibly fast. Because of this GPS-like branching system, B plus trees completely eliminate a massive chunk of the search space at every single level you drop down. In computer science, this kind of lightning-fast retrieval is known as O log n time complexity. To put this into perspective for you, if you have a database of 1 million records and each node in your tree holds 100 keys, mathematically, it takes just 3 steps to find any specific record. Just 3 steps to search 1 million items. That is literally the pure magic of computer science at work. But look, even with the best map in the world, physically fetching data from a hard disk is still relatively slow. To get around this, databases use something called a buffer manager. This acts as a bridge between your server's RAM, which is lightning fast but pretty limited in space, and your disk storage, which is massive but, slow. The database caches the most frequently accessed data right in the RAM's buffer pool. So if the data for your headphones happens to already be sitting in the buffer pool, a scenario we call a cache hit, retrieving it is practically instantaneous. All right, moving to section 4, guaranteeing data safety. Let's talk about the absolute worst-case scenario for an online store. What if the server suddenly loses power exactly halfway through processing your payment? Your bank gets charged, but the actual order never generates. Yikes, right? How do databases prevent this nightmare? Well, they rely on 4 fundamental pillars of data safety known as ACID compliance. That stands for atomicity, consistency, isolation, and durability. These rules govern database transactions, ensuring that your data stays entirely valid even if the system crashes, throws errors, or if 1,000 other people are trying to buy the exact same headphones at the same time. So, the crucial point to understand here is the A, atomicity. Atomicity dictates that a transaction is treated as a single, indivisible unit. It's a strict all-or-nothing guarantee. In our shopping example, withdrawing money from your bank and depositing it with the store are permanently linked. If the server crashes right after the withdrawal, but before the deposit goes through, atomicity ensures the entire transaction is rolled back. It's basically as if nothing ever happened. Consistency and isolation do similar heavy lifting to ensure data rules are followed and concurrent shoppers don't step on each other's toes. And a guarantee, the D, durability, which means that once you get that confirmation screen, your order is permanently saved, even if a clumsy intern trips over the server's power cord a second later. Databases use a write-ahead log, or WAL for short. Before the database even attempts to modify the heavy main data files on the disk, it quickly jots down a tiny note of the transaction into this sequential log. If a crash happens when the system reboots, the recovery manager simply reads the write-ahead log and reapplies any changes that hadn't quite finished saving. It's a lifesaver. And finally, Section 5, scaling the system. Everything we've talked about so far works beautifully for a normal, everyday website. But what happens when your store goes completely viral and suddenly a single server just cannot handle the millions of queries hitting it every second? When a single machine hits its limit, you have to scale. Historically, relational SQL databases scale vertically. That basically means you just throw money at the problem. You buy a bigger, more expensive server with more CPU, more RAM, and more storage. But eventually, you hit a physical ceiling. NoSQL databases, on the other hand, are largely designed to scale horizontally. This means you just add more standard servers to your cluster and distribute the data across them in a process known as sharding. It splits the workload up, allowing for practically infinite scale. Let's zoom out a bit and see how this all builds into the broader design philosophy of databases, which was defined years ago by the ANSI Spark architecture. This standard elegantly separates a database into 3 distinct levels. You have the external level, which is just what the user sees. the conceptual level, which is the logical structure, like the tables and relationships, and the internal level, which is how data is physically stored on the hardware. This separation is brilliant because it means an engineer can literally swap out the physical hard drives at the internal level without ever interrupting your shopping experience at the external level. Okay, as we wrap up this explainer, let's quickly review our core takeaways. Databases are highly specialized engines built to securely organize massive amounts of data. Every time you interact with an app, your queries follow a strict pipeline, from tokenization all the way to execution. Under the hood, genius structures like B+ trees make searching through millions of items happen in mere milliseconds. And through it all, ACID properties and write-ahead logs are standing guard to protect your transactions from the absolute chaos of network failures and power outages. It is truly remarkable when you step back and really think about it. Every seamless click, every effortless online purchase, every single digital interaction that we completely take for granted, it all relies entirely on this highly optimized, invisible choreography of data. So, now that you understand how the engine actually works under the hood, what will you build with it? Thank you so much for joining me on this explainer. I hope you found it as fascinating as I do. Keep learning, keep exploring, and I'll catch you in the next one.